All right. Good morning, or good afternoon, good evening, and good night, everyone. Today is our bi-monthly webinar series for the digital Earth is over on the high-resolution land model and land-atmosphere coupling. My name is Min-Hui, along with Andrew Gettelman and all previously participate scientists that we try to get the community involved on these high-resolution land models. The necessary try to communicate with this community, try to see how we can improve our understanding of these high-resolution land models. Then try to develop these high-resolution land models and then atmosphere coupling, try to emphasize the 3 points that I listed here, especially this knowledge exchange that we usually have. And in the previous webinar series, we have a lot of serious discussions on various topics. So it's very nice that we can continue this webinar series. And I would like to have Andrew Gettelman to say a few words. Andrew, please.
Sure. Thanks, Min-Hui. Thanks everybody for coming. It's great to see everybody participating in this. I'm co-chair of the Digital Earth Lighthouse activity for the WCRP. This is one of our activities. We have an active seminar series in this. We're also planning a number of other events, including a sort of hackathon on high resolution models. So you can go to our website to find out more about that. That will include land models, and there will be data sets available for the sort of land atmosphere coupling and looking at things at high resolution. So we're pretty excited this community is active, and we hope to be able to foster that a little bit more as well. So thanks for being here, and thanks for organizing, Min-Hui, and thanks Lingcheng for giving a talk.
Thank you.
Cool. Thanks, Andrew. And today is our pleasure to have Dr. Yifan Li to share with their group's recent findings on this high-resolution land models data set. So Yifan, you can share your PowerPoint file if it's ready. And this data set can be very useful for how we can advance to the kilometer modeling, and since it provides a very critical boundary information. Okay, so right now I would like to quickly introduce Yifan. So Yifan graduated from UT Austin back to 2020, and he got his PhD over there. And later on, he worked as a postdoc in PNNL, and later a research scientist over there till now. So in his research career till now, most focus on how the land atmosphere couples, and then how the land surface process impact the atmosphere, and also the hydrology, land hydrology as well. So today he will share with us how this kilometer scale can be further advanced and go into like using more detailed land information. And some of the case studies, I think Yifan will also share with us. Yeah. Okay, Yifan, please, all yours.
Okay, is my sharing okay?
Yes.
Okay, yeah, thanks. Hello, everyone. Thanks for the invitation. So today I will cover the developments and the case studies in the kilometer scale land surface modeling, and share some of my work at PNNL in the past several years. So advances in computing power nowadays allows us to simulate the Earth system at kilometer scales. I refer to as a K-scale in the following presentations. So in the K-scale atmosphere modeling, they can capture detailed cloud structures and also the weather phenomena like the MCS. And in the ocean kilometer scale modeling, as the resolution increases to K-scale, it can better capture and understanding the circulation systems and the coastal impacts. And Nanosource model is also moving to the kilometer scale resolutions, like example here to show the global model inverse the 1 kilometer planet routing depths. And recent years, the machine learning in digital twin and is developing very fast. So here is an example showing the NVIDIA S2 simulations. Animation shows the kilometer scale simulations. When we look more closely over the land surface, and this is our focus today, and we see a lot of varieties, the mountain terrains with complex topography and rivers around it. And then in the desert regions, you can see the agriculture grows where irrigation creates green patches. In the rainforest, deforestation breaks up the dense vegetation with the clear patterns here. And also urban landscapes show the mix of buildings and green parks. So highlighting the diverse land use in these details. So K-scale modeling is needed to capture all these details and also represent the fan-scale process at K-scale modeling is essential to better understand all these changes and dynamics. With these benefits of the K-scale modeling, however, there's still challenges on the current challenges. Firstly, we still lack integrated K-scale land surface parameters for the model configuration, and then we don't have enough benchmark data set at K-scale for model evaluation. And also the forcing data drives the land surface model is also lacked in K-scale high resolutions, and representing some of the underrepresentation of fan-scale process like lateral flow is still not common in assessment models. And also we need to calibrate or recalibrate some of the parameters in the models that are settled for the coarse resolutions when we move into the K-scales. So build upon these challenges, in my talk today, I will first talking about developing K-scale datasets to enhance the land surface modeling, simulation, and evaluations. So this includes the K-scale nanosurface data parameters for model configuration. And the second, I'll talk about the K-scale machine learning based dataset for evaluation. And then for the atmospheric forcing, I will talk about applying the generative AI to develop K-scale climate forcings. So let's start with the 1 kilometer analysis. Then in the second part, I will talk about the K-scale ELM simulations of corners. So we will use the ELM, which is a land model of US DOE Energy X-scale access model. So first we will perform the spatial scaling analysis on the soil moisture simulations of the entire corners at 1 kilometer scales. And then we will run the ELM simulations with model calibrations to increase the accuracy. In the third part of my talk, I will briefly talk about the representation of natural flows. So I will introduce two developments in ELM. One is the quasi 3D lateral flow ELM natural, and the second is the tightly coupled 3D lateral flow ELM phase path flow. So let's start with the development of K-scale nanosurface parameters. So commonly, currently used nanosurface parameters have several limitations. So using CESM, default nanoparameter as example here. So they are often coarse resolutions. For example, the LAI is at 0.5 degrees, and the data source usually outdated, part of them processed more than 10 years ago, and the temporally are static. For example, the nanocover is only for a given years, don't have multiple year to check the changes. So to address these limitations, we developed the new nanosurface parameters. So we moved from the coarse resolution to 1 kilometer globally, and we use the most up-to-date and well-validated data source to prepare the data set. And also the data now is spanned from the 2001 to 2020, and we continue to extending. So the data processing is done like with the Google Earth Engine, which is very powerful tool to handle big data. So in the new 1 kilometer global land surface parameter includes 4 types of data. The first is land use, land cover, includes yearly, plant function type, and other land cover types, urban, glacier, lake, and also the vegetation properties of the monthly LAI, stem area index, and canopy height, and also the soil properties and the soil texture of soil organic matter, and also the topographic indexes of elevation, slope, and also some new top index like we are developing an aspect, scale view, and terrain view. All these are included. So here is a global view of the 1 kilometer land use and land cover data for the year 2005. So you can see the detailed distribution of different plant functional types and also land use category like glacier, lakes, and also some cities, urbans. Here is the leaf area index globe map. So the red color means like high valued, blue color means low LAI. So when we zoom into 4 locations, the first one showing the mountainous regions with complex terrain, and also you can see varied LAI. And second is the rainforest deforestations. You will see the patterns, bands, like with reduced LAI in the deforestation area. And this is an example in the desert irrigation. You can see how the irrigation will create an increased LAI in the around desert. And this is the example is the urbanization will also change the LAI patterns or the vegetation distributions. All this can show the detail in this data set. So here is the showing the map of the canopy height, percentage of clay soil texture, the topographic index of standard deviation of elevation, and the slope. Next, I will show some comparison between the new data and the existing commonly used data. So there are 2 like existing data. One is from the CAR 2012 study. Another is like CSM or CLM5 default data set. So this map, this figure shows the land cover comparison air fractions, and you can see there's like clear difference, especially for the like bare soil. You will see 3 different data sets have different ranges, and also the brownleaf evergreen trees, and also the sharp types. This is like our show the comparison of leaf area index. So you can see overall the global patterns for these 3 data sets show similar patterns and with a similar global means. But when you calculate their difference, you can see the obvious difference and show larger variations. So generally, like new data set has relatively smaller LAI in the boreal and relatively larger LAI in the tropical regions compared to the existing data set. Then next, like after talking about the kilometer-scale land-surface parameters, I will talk about how to develop the K-scale machine learning-based soil moisture for the K-scale land-surface modeling evaluations. So this is like we built MNander, a machine learning augmented database for Earth and environment research. So on the left side is part of our framework. So we use the predictors from the meteorology, vegetation, soil property, topographies, and hydrologies. Some of these variables are from the previous developed the 1 kilometer dataset, and then we also use the in situ soil moisture from the International Soil Moisture Network observation as the target variables, and we use these variables to build the auto machine learning models and performs the explanable machine learning analysis. And then we apply this model to generate the daily soil moisture at multiple layers across the entire corners. So here is an example to show you that the data set that we developed at 1 day for the soil moisture, you can see a lot of more high details if we zoom in. Yeah. So the third part of the dataset we are developing is using the K-scale generative AI downscale climate forcing. So generative AI is a very powerful tool and a cutting-edge machine learning method. So in this study, like we develop these generative AI models and use the US Mid-Atlantic region as the case study regions, and we develop the dataset for 4-kilometer hourly resolutions and for both historical and future projections. So this will be very useful to assess the climate change impacts. And we use the CONS4 for the training dataset, which is at 4-kilometer hourly resolutions. And then we to build the Cheng and fine-tune the generative AI model, diffusion model, and then we apply it to coarse resolution climate model, for example, the CMIP models, and to generate the kilometer-scale atmospheric forcing. Here I show some preliminary result for the air temperature, precipitation, ultraviolet radiations. So in the third row is the generative AI downscaled forcings, and the second row is the choose. So from here you can compare the second row and the third row. You can see that the generative AI can really capture the observation or choose very well, and we show some detail patterns also captured. Now, let's move to the second part about the simulations we are doing over the entire corners, and we will use the ELM model. So firstly, I will start with the spatial scaling analysis of soil moisture simulations. So use the 1-kilometer global new data set. We set up the model run at 1 kilometer over corners using the GSWP3 forcings. And this map shows you the simulated soil moistures with very high details. But you may find that there are some still coarse patterns. This is because our forcing data is still 0.5 degrees. So which means the high resolution forcing data is also very important. So these two subregions highlighted here I will use to demonstrate the spatial scaling analysis. So for the spatial scaling analysis, we picked a 0.5 degree subregion box, and we calculate the standard deviation of the 1 kilometer soil moisture simulations. Then we upscale this 1 kilometer dataset, 1 kilometer simulation to 3 kilometer, and then we recalculate the standard deviation of these subregions, and we calculate the relative difference of the standard deviation compared from 3 kilometer compared to 1 kilometer, which means the spatial variability changes during these upscales. And we can expect that the standard deviation will decrease. So by quantifying the decrease of the spatial variability, we quantify it as the information loss. So with the up to 6 kilometers, so calculate this standard deviation again, and upscale to 12 kilometers and calculate standard deviation. So from the 1 kilometer upscale to 12 kilometer, the standard deviation will decrease about 55%, which means about half of the spatial heterogeneity information are lost when you compare the high resolution versus the coarse resolutions. So here I show the example for a region with high information loss. So this is another subregion with relative or no resolution, no information loss. And then I'll show you the entire corners map. One is for the 1 kilometer spatial variability. Another one is for the when we upscale to 12 kilometers, how the information loss looks like over the entire corners. So here is the spatial variability map. You can see some larger values here with larger spatial variability across most of the corners, and highlighting the K-scale parameters or K-scale modeling value because it can provide you high spatial variability, high spatial informations. And then we use the attribution analysis to attribute which factors can determine the spatial patterns of the spatial variabilities. And we find that the soil properties, clay, sand, clay, percentage, and also the precipitations are the major factors driving the spatial pattern of the spatial variability. And then this figure shows you here the information loss when we upscale 1 kilometer resolution to 12 kilometer resolutions. So overall, from the entire corners, there are about 30% information loss when we do the upscaling for the soil moisture. And similarly, like we attribute and find that the soil properties and also the temperature are the major factors driving this spatial pattern of information loss. We also compare our soil moisture simulations with benchmark dataset at relative close resolutions. You can see that there's obvious biases, overestimate or underestimate of the soil moistures. So of course we know that the soil moisture benchmark also has uncertainties, but the point is that even we have the K-scale nanoscale parameters, so itself alone doesn't guarantee accurate simulations. So next, I will show larger columns simulations, but this time by doing the calibrations to improve the accuracy. So in this study, we run the model of the entire class, is the 1 kilometer global new data set we developed, and we calibrate the models using the water table depths and also surface water fractions. Here is the example, all these to show the water table depth simulations. So the first row is the benchmark data and default ELM simulations and calibrated ELM simulations. The second row shows the biases for simulations. So from when you compare the calibrated and the benchmark, you can see how significant improvements from the calibrate after the calibration for the water table depth simulations compared to default. And from the matrix here, after the calibration, the R-square increases from 0.3 to about 0.8. And if we look at only focus on the shallow water table depth, less than 8 meters, the R-square and the biases decrease from the 14 meters to 0.7 meters. So which means not really improve the accuracy of water table depth simulations. So here is the simulations for the water surface fractions. So this is benchmark. Similarly, this is benchmark, this is default simulation, and this is calibrated. And after the calibration, you can see the calibrated data improves the overestimate of the water surface fractions, and the R-square improved from 0.2 to about 0.7, and the biases reduced from 0.29 to 0.001. So it's largely improved when you look at spatial patterns of the biases. So next, I will go to the third part. So which is the representation of the lateral flow. So I will talk about two methods. One is the quasi-3D lateral flow, ELM lateral. So when we go into the typically 100 kilometer, which is the typical Earth system modeling resolutions, and we go from here to the high resolution at 1 kilometers, we will the hair slope process will become more and more important, and the lateral, for example, the lateral flow, the effects should be very significant, and we cannot we cannot avoid this representation in the K-scale modeling. And here is another study showing that the relationship between grid resolution and the lateral flow magnitude. The x-axis is from the low resolution to high resolution, and you can see with the resolution increases, the magnitude of the lateral flow becomes more and more increase significantly and become more and more non-negligible. So in the default, like most assist models or non-surface models, so in default it is column-based model. It is in the vertical one-dimension column, and the unsaturated calculation and saturated calculation all is based on vertically. And in the ERM lateral flow development, we add the exchange of the lateral flow, include the unsaturated lateral subsurface flow and also saturated subsurface flow. We did do the test at the experimental watershed, showing that you can see that with the lateral flow, it largely improved the water table depth simulation compared to the benchmarks. And without lateral flow, you can see that there's low spaces patterns affect follow the terrain patterns. So which means to go to K-scale, this is similar at 1 kilometer. So when we go to the K-scales, this process rarely needed. So the second example of the development is about ERM phase path flow. And so ERM phase is 1 kilometer, is one-dimensional vertically. So phase here is the vegetation dynamics model, and vertically, and the path flow is three-dimensional, which tightly couples 3D and can consider the subsurface flow, saturated, unsaturated, and also the surface overnight flow together. So after cover them together, we can consider lateral flow. And then we tested this, we applied this model to the typical watershed in the central Amazon. So where the water table depths, this is simulated water table depths. One column is deeper water table depths, green color is shallow. So you can see how the water table depth follows the terrain patterns. And when if around this transit from the plateau to valley, we compare the simulation with the measurements. And you can see from here, the red curve is the simulation, the black dot is the observations. And from the plateau to valley, the deep water table depths to shallow water depths here. So the simulation can really capture from the observation comparison. And now we are expanding this framework to larger scales over the entire Amazon. So the entire Amazon at 1 kilometer is about more than 55 million grids. And this is a preliminary result showing that after 200 years spin up, you can see how the water table depth looks like. And when you look at details, it shows the preliminary result with reasonably of the water table depth simulations. They can show the water table depth is shallow around the rivers and also around the valleys. So yeah, so in summary, from my talk, I talk about the below several aspects. At first, the kilometer scale land-surface parameters, benchmarks, and forcings are essential for land-surface simulations and also to capture the K-scale heterogeneities. And the K-scale parameter alone, as you can see from our studies, doesn't ensure the accurate K-scale simulations. So calibration is one of the important method to improve the accuracy, and also with the K-scaled the coarse resolution, K-negated process at the coarse resolution need to be explicitly represented at the high resolution K-scales. So we show the example to represent the lateral flow can enhance the K-scale modeling. And also you can see AI ML is very powerful tool and is useful to advance our K-scale land-surface modeling. So we did some I shared some study we are doing, and also there are still many opening questions that we need to further investigate. So, and also of course looking forward to discuss with all these questions. For example, what science questions can K-scale modeling address, but low resolution cannot? What gaps remains in the capability of the K-scale modeling? and what are the key processes is represented or missing in K-scale modeling, and how we can leverage the AI ML to enhance our K-scale modeling, and how do we use some methodology like data assimilations or parameter calibrations to improve the accuracy of the K-scale modeling, and how we can balance the complexity versus the computational flexibility. We know that K-scale is calculation is still time consuming, and what interdiscipline calibration is needed. So with that, I would acknowledge my advisor, mentors, and collaborators from my work, and also many others that's listed here. And my talk today is covered from 4 projects. First is the U.S. Department of the Energy integrated coastal modeling, and from the US DOE next generation ecosystem traffickers, and from my co-PI project, I'm Nander, and the PI project, Icon, to develop the generative AI downscale forcing. So yeah, thanks for your attention. So if you have questions, please reach out to me. And here is some reference I'll attach it here. You can read more for details, and look forward to the discussions with you. Thanks.
Thank you very much, Lingcheng, and to give us this high resolution data set and showing how this high resolution length parameter can improve these simulations. It's pretty nice. Thank you very much. So you can, the audience, you can either type your questions on the Q&A or chat box, or you can raise your hand, then Lingcheng will address those comments or questions that the audience have. Lingcheng, there are actually 2 questions now, one in chat box, the other one in the Q&A box. Can you see them now?
Yeah, I can see one in the chat box. So
Yes.
the question is the big difference in the Bell soil between the new and the K-12 data based on the observation, was compare the interpretation of Bell soil in the original observation? Yeah. So let me go to here.
Yeah, I think in the beginning it shows K-12 comparisons.
Yes. Yeah, and you mentioned the Bell soil, so it is in here. I think you can still see my screen.
Yes, it's not full screen though.
Oh yeah,
I think still can.
Okay, yeah. So oh yeah, maybe in this mode. Yeah, this mode. So you can see from the blue color is the new data set, and the orange color is K20 12, and the red color, the green color is from the CLM default data. So the larger difference is between the CLM default and the new or K12. So
I think Su-Hao also mentioned how about the new and the default one. The new one and the default one.
Is so firstly, the default one is developed more than 10 years ago, and when it builds the data set, is at that time the modest data is not that mature compared to now. So there are a lot of improvements during this past more than 15 years. So, and also this default data set is combination of different years of data. Maybe also have this kind of uncertainties when build this default data set. And so the new data set, we use the latest modest 99 cover, so it should be, in theory, should be better than the default ones. Yeah. And when you see if it is compared to observation, so when they build of the modest data, they are built based on the observation, train the model to then apply to Intel Global to have the new data set. Yeah, it is use the information from the observations. Yeah.
Okay. Thank you. And Su-Hao, if you have a further question, you can let Lingcheng know. And Lingcheng, there's another question from the Q&A box. Can you see it?
Yeah, I can see it. The
Okay,
question
yeah.
is, based on what reason you prefer to make recalibration and what result you get? And do you recommend or others to apply on their analysis? Did you apply it on local machine? On local machine, the generative AI? Yeah, there's 3 questions. So let's start from the first one. What's the reason you prefer make a recalibration? So firstly, like currently in assess models, like usually we run the land model simulation at relative coarse resolutions, either like, so the parameters, like for example, some of the parameter in the coarse resolution model, the value of the parameter are settled for the coarse resolution models, or maybe calibrated for the coarse resolution models. When we go to K-scales, these parameters may not suitable, so we need to recalibrate. Why we need to do that? Because we see some like from the preliminary comparison of the soil moisture benchmark, you can still see like a lot larger biases. So this is to show the like preliminary results showing the soil moisture comparison between the K-scale simulation versus the benchmark data. You can still see some biases. So that's why like we think when we compare with observations, we need to do some calibrations. And then we show some study after the calibration, we can do really like improve the simulations we have. So that's why we are thinking calibration is also important. So the second question is, yeah, what result I get yeah, based on the soil moisture and the water table depth simulations and also water fraction simulations, we think it is needed. Oh, the question is not there anymore. So okay.
Yeah, it's the question is a shift to the already answered. You can click the middle one. You will see
okay,
it.
I see that. Do you recommend for others to apply on their analysis? So it depends. I'm not sure understand this question details. Like if you mean the calibration, if you are like doing the K-scale simulations and based on your study like purpose, I think if you, for example, we are looking at the hydrology simulation, for example, water table depths, like we do the calibration and could improve the accuracy. And because they improve this accuracy water table depths, it could also improve the potentially it could improve the soil moisture, hopefully, but we're still evaluating. For generative AI, you applied on local machine on the generative AI. Yeah, we do the generative AI in the the GPUs. So in the supercomputer, yes, this is how we do that. Yeah, and any other has comments on this question, we can share the comments, share the thoughts together.
Okay, and actually, I think the audience also try to mention is why you make the recalibration.
Yeah.
Can you see that there's a, yeah.
Recalibration is because like the very specific is like when we do, for example, when we do the soil moisture observations, the results cannot match well with the benchmark data, and also because like more theoretically, because like some of the parameter is settled for the coarse resolution, because we usually for the assist model we simulate at the coarse resolutions. That value of the parameter may be suitable for the coarse resolution, but when we go to high resolution K-scale, there are more details, more heterogeneities, which may not suitable for that settled parameter value for coarse resolution simulations. Yeah, coarse resolution models. Yeah.
Okay.
Then I'll go to the next
And
question.
yes, please.
So the question is, could you please elaborate a bit more about why kilometer-scale simulation can still have problems? Yeah, so so first, like we have like first there's like large uncertainties. So and the model is very complex. So this is like a background. So like even like we have the more accurate input data, we have the but the uncertainty from parameter may not correct. So we could not guarantee the beta simulations, and also there's uncertainty or not the accuracy from the atmospheric forcing. So this is also very important to consider to have this accurate result. So even you have a K-scale, non-solid parameters, you have the K-scale atmospheric forcing, you may still don't have the accuracy result, maybe because the parameter could be not right. But with this K-scale data set, we have the ability to show the spatial patterns, spatial heterogeneities. It's a starting point, and it could use it to start some questions if you not only look at the accuracy itself. As yeah, we showed some like example of the spatial scaling analysis to show you how the with like high resolutions, when we look at the coarse resolution, how much information we lost during this like from just to emphasize the value of the K-scale simulations.
Yeah, I think the audience also mentioned that this question is also about the 1 km versus 12 km comparisons.
Mm-hmm. Yeah.
Yeah. Okay. Do you have the slide that showing these two different resolutions comparisons? Maybe you
Yeah.
can, yeah.
Here. Yeah, maybe this is okay. Yeah, so yeah, so information loss is like calculated from the 1 kilometer when upscale to 12 kilometer. So why we're doing this, because we want to show that because we in the 1 kilometer we have a lot of heterogeneity and a lot of special informations. But if we only look at the coarse resolutions, these details are disappear. So we just lose all these like informations, especially like for previous talk about the actionable science. So like maybe like for actionable science or applications, we do care about the high resolution. For example, if you have the farmer or the cropland here, but in this coarse resolution, they're not well represented. Maybe you're here, you don't have drought. Maybe here you have a drought, but here maybe it is the same. So you cannot see this information are lost. So, yeah, like this.
Okay.
Maybe I can
Yeah,
go
cool. Make you go to the next question.
So the question is, what data did you use to update your water cover? And how did you introduce time variability? Yeah. So I think you are talking about the calibration. Well, you're talking about the data set itself or the calibration. I think maybe you're talking about the data set. Yeah, so if you are talking about the NAND cover, this is NAND cover for the water surface, like for example, the lake. So because our data source is based on models, it will update the water cover each year. And also if you want more detailed data, you can refer to like I remember that global like water surface data set, like at 30 meters you can use. If your question is related to the calibration, because in the calibration, we mentioned the water surface fractions. So this So we calibrate the data, we calibration because the model itself can simulate the water surface, and we can consider the time variabilities during the calibration or the objective functions. Yeah. Yeah, I think. So
yeah, so I think
yeah.
the second part about introduce the time variability. So it's based on that is because MODIS data provide year-to-year variations. So you introduce these time variance, right?
Yeah, that's correct. Yeah.
Okay.
Yeah, thanks for clarification. So
Okay.
yeah, thanks. So for the next question, still the question is still related to the data, given the high uncertainty some of the data themselves. For example, the soil property data and the calibration seem to be quite efficient. Should we focus more on parameters calibration or for kilometer scale rather than trying to get the background? Oh, okay. Yeah, that's a good point. I think that's good questions. So I can understand. So you mean like we have by calibrating we can also achieve the good result. So maybe we don't need to update the kilometer nanosurface parameter, right? So I think because like when you calibrate things like this is our base knowledge to calibrate the model to have the for example one type depth result. But for example, if you want to study the vegetation variations, even your one type depth is right, but the vegetation part is not right. I mean, the response like GBP or carbon may not right. So which means in terms of your study questions, like you may get the right answer, but due to wrong reasons. But when we update the case scale data set, we just like use our best knowledge to give the detailed patterns of the land surface and land line cover, what sort of properties, all this based on our knowledge, and also then we calibrate the model. So based on all this based knowledge, we just try to get the right answers due to right reasons. Yeah.
Yeah, that's cool.
Okay, I will go to the next
Yes,
question.
please.
So the question is, case scale simulations can provide more spatial details, but does it really provide more accurate simulations compared to coarse resolution simulations? How can we better compare two simulations with different spatial resolutions? Did we upscale the case scale simulation to a coarse resolution? Yeah, that's a good point. So currently, like if we update the case scale modeling, we only update the case scale, like nanosurface data set, doesn't guarantee the better performance compared to the coarse resolution. If we look at coarse resolution, and because as we like mentioned, like the parameter may be not correctly calibrated in the default models, and also with this and also like some of the fine scale process may not represent it. Even I did the case scale modeling here, but some of process may not represent it. For example, the lateral flow. So for most of the Earth system model, land model, or in the Earth system model may not represent the lateral flows. So you may get a worse result if you if you only go to kilometer scale resolution, don't include all these like factors. And how we compare two simulation, yeah, I think this is a good point. Like when we go to kilometer scale, high resolutions, how to what kind of metrics we can use to evaluate this, because case scale like benchmark data is not that enough compared to coarse resolution benchmark data, and also the case scale data benchmark may have some uncertainties. So how to evaluate this case scale? I think like one way, as you mentioned, like maybe we can just quote it out to coarse resolution compared to with the coarse resolution modeling. Another way we can capture some of the relationships, for example, the precipitation runoff relationships, how these relationships in the K-scale modeling could be better captured than the closed resolution modeling. So this could some other strategies to show our benefits of the K-scale modeling. Yeah, so I think roughly I answered this question. Thanks. And the next one is the paper and the code open access? Yeah, the paper and the code and the data is in the shared the node. And if you have the questions, you can send me emails. Yeah, when you use, because the data is also very large. It's about over 200 gigabytes. So you can download. But yeah, if you have questions how difficult to download it, just let me know. I can send it to you or crop it to you for you. Yeah.
Nice. So the 200 gigabytes because all cover like 20 years of the data set.
Yeah, 20 years and yeah, globally 1 kilometer. So it's like relatively large data set. Yeah.
Okay, got it. I think you have addressed all the questions. That it's a very nice, and I think no more question for now. Well, anyone want to raise any questions now? I guess there's a quite fruitful discussions, and I think definitely we need this high resolution data set in the future KM scale modelings, especially when we consider this land M3 interactions. Those lateral flow you mentioned, that once consider this lateral flow, it can increase the spatial heterogeneity of the soil moisture. That should definitely have some impact over those local climates and maybe regional climates as well. And I think I really like that you list these open questions. That's definitely a lot of that this community can continue working on this.
Yeah, that's not a question to address.
Yeah, it's cool. Well, I would like to thank Dr. Lingcheng listening again, and thanks for everyone's participations. And we will have another one in the future that we will announce it, and hopefully everyone can join. And of course, if you would like to share your recent research topic and to this community, please let me know, and we will try to arrange this.